Okay, thank you. Thank you very much for the invitation to talk at Cornell. I also, as the other, wish I could be there instead of via this Zoom. And I'm sorry I cannot listen to you because of this coupling problem. But any question, you just say something and Alp will tell it to me. So, and I also want to thank Alp, who is my graduate student that is helping me to video this. So, okay, let me start the topic of the talk. I hope you enjoy it. So the title is this title, Rigidity through Potentials. Rigidity via potentials. And it's joint working. So it's a whole program we are developing with Andrei Gogolev. And its basis is some general theory in dynamics, but it can be formulated in very geometric terms. So let me just give you a somewhat famous theorem by Croke-Otal. So it's not joint work, so it's two independent works. It's in the 90s, maybe 89, 88, and 91. It's just more or less around these times. They show that if you have two surfaces, I surfaces negatively curved, and with same what is called Mark length spectrum, and this essentially means length of homotopic geodesics coincide, then they are isometric. So they can fully check whether these two surfaces are isometric from knowing the lengths of closed geodesics. So since the metrics are negative, there is only one closed geodesic for each homotopy class, non-trivial homotopy class for each surface, and they are asking this length to fully coincide for each guy. So this actually didn't came from nowhere. So this had a even very, very long history, but let me just say things related to what we are doing with Andrei. So the work of Guillemin and Kazhdan in the 70s, they also show pretty much similar statement, but under some sort of deformation theory. So it's not just any two geodesics. So you take a deformation of G1 by a path, and you prove the same statement, but through these deformations. Katok did it in the 80s, early 80s, assuming both are in the same conformal class, so that then G2 is a scalar multiple, non-constant scalar multiple of G1. And so the way we started working on this, other than other also work we had before, is because Andrei was giving a series of lectures on this in Ohio, and Khalil and Lafont asked, so Osama Khalil and Jean Lafont both were in Ohio. Well, Lafont is still in Ohio. Khalil is in Utah, if I remember correctly. So they ask if you can say the same, but instead of having coincidence of length, you have a coincidence of some function, in a sense. So let me put the problem more explicitly. So let me put some name, some definition here that will be useful. So given a Riemannian surface SG negatively curved, okay, I didn't say it in the formulation of the theorem, but you want them to be homeomorphic surface so that they have the same pi1. So I can talk about corresponding geodesics. If not, it doesn't make sense. But anyway, so given a relatively surface and a function phi from the surface into R, we can define two objects. One is L of G phi, which is actually not just pi1, is the homotopy or isotopy classes of curves, but let me just write it as pi1 into R by and little l. So here the capital L G phi of a class gamma is the integral over gamma of phi. So this is gamma g. So this is parameterized by arc length, and you just integrate the guy, and the other is the normalized length. Would be 1 over the length times the integral of phi. So, so we have these two guys. So in the case of Croke and Otal, you will be worried about the function phi being the constant function 1, and the capital L, the small, okay, there is some length. So in the case of the little l, this is, and the function phi equals to 1, this is giving you just always a 1. So it's not so interesting in a sense. And so the question was, instead of the previous one, assume you have functions phi1 and phi2, phi I from Si into R, and you assume that phi they coincide always, and phi2 coincides with this guy. So can you say the same? Can you answer the same? Can you prove the very same statement? Now, of course, you want to make some extra assumption if you don't want to have a trivial statement. So you want to assume, say, phi1 not identically 0. So because if phi1 is identically 0, then most likely phi2 also will be identically 0. Maybe both are identically 0, and you are not getting any information. So you have two surfaces, negatively curved, which the average of phi along any curve give you the same number. So this is not, so give you 0, not just the same number. So this is not found. And then, as I said, of course, if the phi I were fully constant, then this is the previous Otal-Croke. And the whole geometric idea behind this type of problem is that you have your surface and you not just your surface, you have some function on the surface. So you have some bump here, and you are looking on this bump, and the function is fully zero elsewhere, for example. And you have another surface which also have a function and doesn't even need to be just a bump. But let's say it is also a bump. So this is phi 2, this is phi 1. And what you know is that whenever you have a geodesic, go through this bump, so it will measure how much you get there, go again. So the integral along this bump and the corresponding homotopic geodesic, the integral along this bump, is giving you the same numbers. That's for the capital L. For the little l, you can pose the very same question here. L, Gi, Phi coincide. And then it's not just this integral of phi, it's the average, the rate of passage of this geodesic versus what you are counting of this phi. So this phi is what is called a potential when it comes to more dynamical terms or more physical terms. So you can think you are having some temperature function on your surface, and you are just measuring the temperature whenever you pass through this business. And for some reason, you have some agreement. Okay, so I will not answer this question yet, even though we can answer it at the end, but we really struggle very badly to answer it. So you want the phi i's to have some differentiability, as well as the metrics to be somewhat differentiable. So I guess R at least 5 should do, and same R here, the phi I being at least 5 should do the job. So you can think it's infinity here, everything, if you want to care. Now, let me just answer what Guillemin and Kazhdan already answered in the 70s. Let's think that this function phi 1, where is the function phi 1? The function, well, phi 1 were identically 0, which means that for the function phi 1, you have all these integrals are fully 0. Okay? So then, of course, you are not getting any information. But you look at the function phi 2. And what you know from the function phi 2 is that the integral is 0 only along all geodesics, in whichever operator you use, capital L or little l. Okay? Now, Guillemin and Kazhdan already in the 70s showed that this implies that the function phi has to be fully 0. So this is already some sort of rigidity for potentials, which come from Livsic Theorem, actually, but they did their own proof, and my idea is to go a little bit through these dynamical properties and dynamical theory behind the proof of these businesses here. So let me get now into the dynamics behind this problem and what is really the dynamics counterpart of this business. So I will completely switch the setting, and now I will be having two transformations, Ti from Mi to Mi, and two maps, phi I from Mi to R, and I will assume that there exists H from M1 to M2. So here I is 1 and 2, which is a conjugancy, so this will be a homeo. And this will conjugate the two guys. So H compose T1 is T2 compose H. So this assumption of the existence of H, the geometric counterpart is when I assume that the surfaces are homeomorphic, so that they have the same pi 1. So here, for the type of systems I will be caring about, you will also have that if some homotopy information behind the TIs match, then they will be conjugated via the homeomorphism. So at this level, the theories really match very well together. And then the assumptions on the phi I will be that if I take the sum, of phi, I have to be careful because I always mess up of who is who. F is T, T1 K of P. This is the same from here to here up to phi 2. Okay. Compose H, and then H compose T2. So then I guess the H should be here, and this should be here. For every P such that T2K of P equals to P, and let's see, am I doing it right? No, I'm not doing it right. HP should be here. Okay, now we are good. So this is the same, and here both functions L fully match. So I could divide by the length of the geodesic, but it's the same n, so there is, or periodic point, so there is not really any difference here. And this is the matching of the potentials phi 1 and phi 2 along periodic orbits. And then I'm in a pretty much same setting, and the question is, then is, yeah, 1, and this is an n, and this is actually an np. So for every periodic point. Then the question is, under these assumptions, plus more, can we say that H is a diffeomorphism? So the isometry in the previous setting becomes to this diffeomorphism statement here. So what's the idea in this dynamical system business? So you have your dynamics, which when you iterate, the time is passing and you are contemplating what's going on. And you have again this potential, which help you see your dynamics, or see your system, see your M. Okay, again, you can think of it as temperature or whatever thing you are looking of it. And then you measure every time 0, time 1, time 2, and so on. And when you make this measuring, this is telling you that over periodic points, you are measuring always the same. And the question that is being asked has the idea behind that if the outcome is being the same always, is because these two systems are not just conjugated, but conjugated by a diffeomorphism. So they really have to coincide at a very deep level. Of course, you want the inputs, if you want something like this, to be at least C1, because if they are not at least C1, then why any topological statement will imply any differentiable statement? Well, sometimes this happens, but you want the phi i's to be CR. Of course, you want the TI's also to be CR. And you want the nice theory to happen, so you want some hyperbolicity on these TI's as well, though the question is much more general. So then let me put the intermediate theorem that clarifies these conditions on the potentials. So you have your function phi1, which your dynamics T1, you have your function phi2, which your dynamics T2, and you can bring, so here is the dynamics T1. In principle, here I have the dynamics T2 in M2. And when I do F phi2 composed with H, I'm bringing this potential into this world. Okay? And so I could forget, if I want, for a second about this second dynamics. After all, they are conjugated. And I'm thinking that I'm having two potentials over the same first dynamics, which are measuring the same along these periodic orbits. And then there is a theorem by Livsic, which says, again, in the 70s, which says that there exists U from N1 to R such that phi1 minus phi2 composed H is U minus U composed T1. Of course, there is a hypothesis here, so it is assume T1 is hyperbolic. Or expanding, which I will define later, but don't worry, it's the standard notion of Anosov or expanding map. And I need to assume H is Hölder, which in general is automatic, and the phi i's also Hölder. And then U is Hölder. So this you can think of your assumption. So these two potentials coincide up to what is a coboundary, which will vanish when you compute along periodic orbits. And in general, if you write down your iteration, you will get U minus U composed T1 to the n, which is some bounded amount, because U is continuous, and then you have the other guy. So this is T2K composed with H. Of course, for periodic orbits, this vanishes, but even for non-periodic orbits, this stays bounded. And that's the type of agreement that you get from phi1 and phi2. So it's some coarse agreement. So in a coarse sense, you have that these potentials are measuring you the same. And then you want to claim, and let me state the theorem. The easy to state, then I go to a little bit harder. So it is Andrei and myself, which says that let Ti be from the circle to the circle, the CR maps are larger than 1. Assume that f prime of x, of Ti prime of x is larger than 1 for every x. So these are the expanding assumptions on the function, and assume the phi I are CR, again, same differentiability, and degree of T1 is the same as degree of T2. And let's erase Livsic. Mi is just S1. So then we assume the matching along periodic orbits. So well, then is the standard theory that says that there exists H from the circle to the circle such that H composed T1 is T2 composed H. And if there exists U continuous such that U minus U composed T1 equals to phi 1 minus phi 2 composed H, then either 1, H is in CR, so H is as smooth as it has to be, or 2, phi 1 was 0 essentially, or constant. Because if phi 1 is constant, then phi 2 is also constant, and there is no much information to extract from the potentials. I'm just saying n times a constant equals to n times a constant. But again, this has to be stated through these cohomology i's. So there exists ui in CR such that phi I equals to ui minus ui composed pi plus ci constant. Actually, the constant is the same. So either the potentials were not giving real information, so it was not really a potential, it was a constant function, so you were doing nothing, or the dynamics are the same. Actually, once the dynamics are the same, you can make up to some co-boundary again, the phi i's fully coincide. Once you reach this level, if you go back to your geometric problem, in the geometric problem, you were getting better than this. You're getting phi I fully constant, but this is, as I said, is Guillemin-Kazhdan type of statement. So if the function is constant along all periodic points, actually 0, then it has to be 0. But this is a property of surfaces, of coming from geometry and the geometric problem. So it will never be true in this generality of dynamics. Now, this theorem in dimension 1 is actually quite easy to prove, quite direct, and it goes back in a somewhat different situation, but still in the circle, to a theorem of Shub and Sullivan. Actually, they prove more and less, so the setting was slightly different, but essentially they prove it in the case phi i's were log of ti prime. And then in this case, as I said, it really is different setting. So you would need the ti's to be C2 in order that these phi i's be at least C1. They can do it in a situation which is it is just C1 plus Hölder. But more importantly, they can do it instead of thinking on this conjugancy H, thinking on maybe other conjugancy which is just absolutely continuous as absolute continuous function on the interval. So, and they can still recover essentially the same result. So this again is in the 80s. And again, you have to think this statement as in the same line of reasoning as Guillemin-Kazhdan, Croke-Otal, Katok. There is also a theorem by Feldman and Ornstein for flows on dimension 3, and also flows in dimension 3, which pretty much do this same work. And there is also work by the Llave-Marco-Moriyon for Anosov diffeomorphisms in dimension 2, doing the same business. So let me give you a proof of this. Yeah? Okay, good. So let me give a proof of this statement. So there is a step 1. Okay, there we go. Oh, good. Yeah, that's actually a very good question. What's the significance of this very specific potential? This is actually has a name. It's called the geometric potential. So the reason for that is comes as well. It has its relevance in these geometric terms. So in the case of the geometric situation, this potential corresponds to the solution of the Riccati equation in geometry. Okay, so you have your metric, you negative curvature, you have your Jacobi equation, and associated to your Jacobi equation, you have your Riccati equation, and the solution of your Riccati equation is pretty much this log of, well, not Ti prime, so you take derivative along the unstable direction of this flow, and that's the same business. But in this one-dimensional dynamics, the reason for this is what is called equilibrium measures. And there are two very important properties for this guy. So property 1 is that the integral of this guy, let me just do d, let me call it this way, 1, this is the entropy of this guy. The same for the Ti, so it's for both guys. So this is the first thing. Now, what is this lambda SRB? This lambda SRB is absolutely continuous with respect to Lebesgue, so to dt on the circle. And not only this is true, but this is actually a maximizing, or well, depending on how you think, or minimizing, depending if you think on left or right. So anyway, so you have always this inequality, and the only measure where you have equality is this lambda SRB. Now, if you think in these terms, actually, the proof of Shub-Sullivan is just one line left. It finished in a second. And that's why what was so important, this log of Ti prime here. You see, because once you have this beautiful characterization of this potential, this geometric potential, by being the guy to which it is associated this absolutely continuous measure, and it's not just absolutely continuous, it's equivalent to dt, and the Ragadon-Nikodym derivative is Hölder continuous. The second thing you realize is that when you push this measure for one guy, will be the other guy. Because there is this nice dynamical characterization of this measure, and this type of integrals are not affected by these formulas. So when I push the measure from here to there and I do everything, I will get that for the T1 I have this formula, and also for the T2, but now for the push of this measure by h, and then it will have to coincide with the other. But then if you have a homeo that sends an absolutely continuous measure to an absolutely continuous measure, the homeo is actually absolutely continuous, and even better, the derivative of this h is pretty much the quotient of the Radon-Nikodym derivatives of these two functions with respect to dt. And so the derivative of h is continuous, which means that h is C1 plus Hölder. So that's essentially how Shub-Sullivan proof goes. And that's why also it is slightly more difficult if you go to a different potential, if you try to follow the very same proof. Because if you try to do the very same potential, the different potential, you still will have some functions phi I. So then it is not true that there is something called the pressure of the function, and this measure will maximize this left-hand side formula. So you have the inequality always, and then you have the maximizer, and you will have the matching also here by the very same reasons. Now the problem is that what you lose is this absolute continuity of this guy. So lambda phi I is most likely singular. So that's why you have to argue somewhat differently if you want to go to this different. And I want to repeat, the idea goes pretty much the same as in the geometric situation. So when you go to surfaces and this purely geometric business, you can argue pretty much the same. So you have this potential, which is pretty much the solution to Riccati equation. You show, so you have to show it, coming from here, that these guys match. Then you will have this sort of SRB, which is you will measure disintegrated along unstables for the geodesic flow, and then you will have this full matching, and then the conjugancy is sending these unstable two unstables, where the Lebesgue measure of the unstable is sent into a multiple of Lebesgue measure of this unstable, which is telling you that your conjugancy is C1 along unstables, then the same C1 along stables, C1 along the flow direction, everything you have to do, but it follows. So you get C1 conjugancy for the geodesic flows. Then, of course, in this geometric world, the proof is not finished. You have to argue that this C1 conjugancy is essentially, actually you have to work a little bit to end up this essentially, but is essentially the derivative of the isometry that you are supposed to be showing. And that's actually a very non-trivial step. And in higher dimensions, it's not understood. So there are some recent proofs by Guillermo and Lefebvre and other people in higher dimension hyperbolic spaces of how to do this in higher dimension, but it's really much harder. But then you face the same problem. So instead of taking the length spectrum, you are taking another function phi. Then you lose all this business, and you have really to go and recover the information. And so what we did with Andrei is first try to understand this expanding map situation, which is somewhat simpler, at least to treat, and then try to see if the same proof worked in this geodesic situation. And actually, we were very happy because it was very successful until we found that we had a mistake in the proof. So for the expanding map situation, our proof, we had two proofs actually for the expanding map situation, one for one dimensions and the other which will work in any dimension. And the proof that only works in one dimension actually can be translated into this metric and geometric problem. And the other one, we still are trying to see how to make it work in this situation as well. So, but I still want to write down the proof of this one-dimensional version of what we did with Gogolev in expanding map situation, because I think it may shed some light of what's going on. So let me now, so this was proof essentially of Shub-Sullivan, and then I want to discuss how is the proof of what we did with Gogolev. So let me go back to the settings. So we have T1 from the circle to the circle, and T2 as well. You have your phi1 here, you have your phi2 here, and you know that phi1 minus phi2 composed H is U minus U composed T1. So the step 1, and you have your H, no? H composed T1 is T2 composed H. So the step 1 is to modify the little phi1 to capital phi1 and the little phi2 to capital phi2 to get rid of this function u, which is the ugly guy here. Or the phi i's is and this ui RCR. So everything here, so everybody is in CR. So this is step 1. Then step 2 is very easy, because it says that if phi2 prime at y0 is different from 0, then take x0 so that this is y0, and then h of x is phi2 inverse composed with phi1 in a neighborhood of x0, which in particular belongs to C1 because you can inverse, so this is inverse function theorem. And then step 3 is use that pre-images. So let me just put this way. So there exists an n, so neighborhood u of x0 so there is one iterate of u that gives you the whole circle. So once that h is C1 or CR actually in the neighborhood in this open set, it becomes C1 or CR in the whole circle. So step 3 is using iteration. Step 2 is implicit function theorem, and then the question is, what is phi1? And phi1 is, in a sense, the same argument that I was telling for Shub and Sullivan, but instead of using the matching of the equilibrium measures, which are not absolutely continuous or they are not so useful here, it is the matching of a different object associated to the little phi i's. So you have this function phi I, and there is a theorem by Ruelle, Perron-Frobenius. Well, it's actually Perron-Frobenius is the standard one, but this Ruelle-Sacksteder. Okay, I don't know how to write these old names. And oh boy, now I really make myself into a very complicated. I should have. Okay, I'm very sorry. This is a Polish guy, and it has a lot of R's and things. Okay, so it's again a theorem in the 70s that says that given this phi I in CR, actually, you just do it for one. There exists a unique capital phi in the same differentiability such that there exists ui as well in CR. Ui minus ui composed Ti is phi I minus phi I, so the potentials are homologous, so you can use them indistinctively for this problem, and with the property, well, plus some function, which is actually the pressure of phi I, some number, I'm sorry, and such that the sum with y in Ti inverse of x of e to the phi I of x of y is equal to 1. So there is a way of normalizing. So this is called the Perron-Frobenius operator. So this is, and this is saying that the eigenfunction, the positive eigenfunction for the Perron-Frobenius operator is 1 and the eigenvalue is 1. So the P would be the eigenvalue, so I take it out, I normalize, and I have all these normalized. And there is this uniqueness here which tells me that if I have two functions which are homologous, like the phi 1 and the phi 2 compose H, the outcome, capital phi 1, will be the same. And from there, you get step 1, just as trivial as it can be. Now, if you want to move to higher dimensions, this theorem is purely higher dimension situation, so there is no one-dimensionality in this theorem at all. So step 1, you get, without any problem, in any dimensions. So you can have full matching of the potentials. And H is still unknown as it is, but now you have these two guys smooth. Step 3 is also in any dimension. So there is any open set, when you iterate enough, it covers everything. So that's the expanding situation. Now the problem is with implicit function theorem or inverse function theorem. So in dimension 1, it's just one non-zero derivatives. In higher dimension, you don't have enough. And actually, the theorem as stated is hopeless in higher dimensions. So you can have some ugly situations with some vibrations and all sort of business that you have to take into account. And actually, that's what we do. So I will not going to make you suffer that. So it's two blackboard statements which cover all possible situations and give you a satisfactory answer in all situations. But it's essentially how to make this implicit function theorem work in any dimension. Now, instead of doing that, I will make you suffer in a different way. So I will give you the second proof of this same theorem in the circle, but it's the proof that you can generalize into the geometric problem. Okay? So the second proof. So the idea is very simple. Then you have to make the idea work. That's not so simple. So you have your H from the circle to the circle. You have your Ti's and your phi i's. Then what you really would like is, so you have this formula. Actually, I want to write it a little bit different. So that's the formula we have, which relate the phi 1 and the phi 2 compose H. And one way of thinking is, what I want is to split this U. So I want to have U as being U1 plus U2 compose H. So this U is only held there. And the reason why this U is only held there is because H is only held there. So phi 1 is CR, phi 2 are CR. So these two functions are very smooth, but since H is not smooth, once I compose a smooth function which is not smooth, I kill the smoothness, and then I subtract phi 1, I still kill the smoothness. So I'm not having U. But if I could split the U in this way, I would make, hopefully, U1 smooth, U2 smooth, and the lack of smoothness of this U comes again from H. So it's just a matter of respecting where you are coming from. And the question is how to do that. Then you try to think this as a two-variable problem, okay? And forget about the H, and you look at this equation. Now it's a capital U. Now the question is how to solve this equation. So try to solve this equation. Now the good news is that now the data, which is phi 1 minus phi 2, or phi 1 and phi 2, is a CR function. The bad part of the problem is that it's almost hopeless to solve this equation. So you will not be able to solve it, most likely. So, but you know you can solve it to some extent, which is on the graph. You have the graph of H, which are all the points x, h of x, in the circle, and the circle. There is a graph of H, which is an invariant set for these product dynamics. And so on this invariant set, we can solve this equation. And the question is, can I spread this information further? Okay. The answer is yes and no. And that's pretty much the game. So yes, I can prove a little bit better than just the fact that this equation has solution on the graph, which is the solution I had before on the graph. So this function on the graph, U, can be extended outside from the graph. That's topologically is trivial. But I can do better than that. It's due to the fact that these two data are smooth. I can show that there exists a function U from S1 times S1 CR such that when I restrict to the graph, so when I do x h of x, this is U of x. So this is a Whitney extension theorem. So this is telling us that the little function U, if I think it as a function on the graph, it is Whitney CR. And that we can prove. Again, it's not trivial, but that can be done. This was essentially, this type of game was already played by the Llave, extending functions on some invariant sets to ambient spaces. Then I have this function on the graph, u. Well, actually it's everywhere, but it does some job on the graph. Okay, that's all I need. Now I look at this expression here. So this by 2 of y minus u, or is it plus u of xy minus u on t1x t2y minus phi 1 of x. So I get this expression, so this function on two variables. And I know this function on two variables vanishes on the graph, and it's CR. Now I can apply again implicit function theorem. Okay? So, which means that if some partial derivative of this guy is not zero, so the gradient of this guy is not zero, then the level set of this guy is a smooth curve, but I know that this vanishes on the graph, which means that it has to be 0 on the graph, which means that the graph is a CR curve. Now, the other way of thinking is, if the graph is not smooth, then it means that this function is not just vanishing, it's vanishing up to the first order. And actually even more, second order and so forth, if I can differentiate more, but at least up to the first order. Then, if I vanish it at the first order, I'm getting more information than just vanishing on the graph. I can differentiate this along the horizontal, along the x direction, and still get vanishing. But when I differentiate along the x direction, this guy disappears. Then, of course, appears some derivatives here, and I have a different equation, which is a little bit more complicated, but I can solve for the derivative of phi 1 some equation. Same if I differentiate along the vertical direction. And that's the information I'm getting. And, well, one can push this business and show that either the graph is smooth, and hence H is smooth, or the phi 1 is homologous to constant. And, well, this proof, if you make the corresponding adaptation, it can be used for the geodesic flow on the hyperbolic surface, and from there you can prove the statement. Okay, so that's it. Thank you very much.